Yeah. Good evening, everyone. So, joining hands, let's start off. Great. We'll be starting with a new chapter. Others comes on. Let's start off. Viscosity. So, what's viscosity? There is an opposition. There is an opposition to the relative motion between the layers of the fluid. This is kind of like friction, but in solids we call it friction, and whereas in liquids and gases we call it viscosity. It's a small chapter. And the force responsible is called viscous force. Others, you guys need to switch on your cams fast. Now, few properties about this. If you increase temperature, viscosity of liquids decrease. Reason, the bond distance increases. Which leads to decrease in interatomic forces. Whereas, in case if you see viscosity of gases, they will increase. You need to understand the difference between a gas and a liquid, right? In case of a gas, the molecules are already pretty far apart. So that thing doesn't matter much. The way the molecules interact with each other is collisions. So molecular collisions increase. They start colliding more rapidly, which leads to more interactions. So the reason why it increases and decreases is completely different. In viscosity, we primarily have only two formulas. Everything we'll derive based on that. Have a look at this page. Let me just take your attendance. Who is missing today? Okay. Clear with this page? So this thing is important. Huh? This is a good theoretical question. They did ask this thing in the exam, bits or mains. That's a bits and mains style question. With increase in temperature, what increases and what decreases? Now, Newton's law of viscosity. I know this guy is there everywhere. So what this thing says, if you have a fluid, and let's say we have a plank here, area A, and if it is going velocity V, the liquid applies a viscous force, F viscous, opposite to this. Let the depth be Z. So the viscous force acting on this plank is given by, it's completely experimental. We'll not get into how we got it. This is given by minus eta A dV by dz. Straightforward formula. Negative indicates opposition to relative motion. A is the area in contact with the liquid. For the fluid. Eta is called coefficient of viscosity. So the units of eta are poise. But the problem with this thing, right? 1 SI unit is 10 poise. That is, in the exam, if they say eta is 60 poise, use eta is equal to 6 while solving. So you're getting in all numericals put 6. If you put 6, you'll get wrong answers. So 10 poise is 1 SI unit. So I don't know why they didn't change that. They could have just kept it better, but yeah. So basically poise is a CGS unit. And this quantity dV by dz is called velocity gradient. That is a variation of velocity with depth. For thin layers, we can write this thing as delta V by delta Z, which is I'll give an example. Relative velocity between two layers by distance between them. Just like V1 minus V2 by Z1 minus Z2. You can do this for thin layers. There, this is the main formula that you can note it down. Now, this thing is derived experimentally. We will going to use this. Like I keep saying every time, we're not interested in how the formula was derived. We are more interested in how we use it. So I have a question here. Can I write that? I can bring that area here, and can I write that F by area as pressure? Because you studied in fluid, right? Force by area is pressure. Can I do that?
Force has to be perpendicular.
Yeah, because what is pressure definition? Force perpendicular to the area. In this case, F is tangential. F is parallel to the area. This is not pressure. This is something else. It's called shearing stress. We'll see later on in elasticity. So this is not pressure. I can write to the next page. Clear? Everyone got this? Palak, Neil, clear with this? Udyan, Ronak, clear? Going ahead. So example. So let's say we have a liquid here. This layer is going with V1. This layer is going with V2. And if this is Z1 and this is Z2. So we write delta V by delta Z is V1 minus V2 relative velocity between those two layers by distance between those two layers. So that's what I mean by velocity gradient for thin layers. This is valid for thin layers. For thin layers, we can assume dV by dz is constant. So for thick layers, it is not. Then this equation F is minus eta A dV by dz. F is parallel to the surface and not perpendicular. Therefore, F by A is not pressure. We call this thing shearing stress. And for the velocity profile, we assume this is mostly true. Velocity of the layer in contact with the fluid has the same velocity as the solid surface. What is the meaning of that? If a liquid is flowing, let's say in a river or something, the liquid layer in contact with the ground will have the same velocity as the ground. So let me show you an example in the next page. Think of like this. Did you ever see a river which is flowing pretty fast? You will still see the fish and the crab or whatever the small things are still, walking on the ground level without getting swept away. The reason being the water level, which is touching the ground surface, is almost having in zero velocity as the ground. So this fish and small animals, right? If they walk under the water, they don't get swept away by the liquid. The liquid is flowing pretty fast on the surface. It is not flowing at the bottom. So whenever a fish has to migrate up the river, they flow under the water. When they want to migrate toward down the river, they migrate, they move on the surface of the river. So like we think, right, the entire river is not flowing in a same velocity. Everything is going in a different layers. So kind of this is how it looks. So if you see the velocity profile, so let's say water in a lake, water in a river. the ground is at rest. So the liquid layer touching the ground also will be at rest. As you go up, the velocity will increase, 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 increase. So if you see the velocity profile, it is not linear. The velocity on the top flows much faster than the velocity at the bottom. Using the same logic, if you take water in a pipe, so what the statement we said? If you are touching the solid, you'll have the same velocity as the solid. So in a cylindrical pipe, how will the water flow? The liquid touching the surface will have zero speed. As you go away from the surface, the speed will increase, 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 maximum. Again, the edges are zero, increase, increase, getting it? And increase. So if you look at the velocity profile, it kind of looks like this. At the center, the speed is Vmax. On the edges, the velocity is zero. This is actually a parabolic shape, again in a gravity-free space. So whenever you're pushing liquid through a pipe, the center of the pipe, right, the liquid is flowing the fastest. The edges are actually going the slowest, almost zero. If you don't think of it this, ever tried dropping ketchup in the plate? How does that ketchup flow? The middle of the ketchup will come down. The edges of the ketchup are slowly being dragged. Always the ketchup which will get stuck is on the edges, not in the center. Same way, ever seen this thing, Tom and Jerry ka thing? Tom sometimes, smokes and releases rings in the air. When it smokes and it gets rings like this. You will see some people actually do this also. They, make rings and release it. How does that work? The idea is, when you have a smoke in your mouth and if you're blowing out, right, the edges of your mouth will behave similar like this thing. Let me show you how it looks. There is this. Yeah. So the edges of your mouth, right, they behave like a container. And then this is what happens. The edges will slow down. So see, when you're pushing the smoke out of your mouth, technically speaking, you should get a disk of smoke, isn't it? But as the disk is coming out, the edges will slow down. The center is flowing fast. After some time, what will happen? The edges will be remaining and the center will go away. And what's left is a ring. So let me show you how it looks. So I'm not suggesting you start smoking. Don't do that. There's a better ways to create smoke. Where are you? Yep. So there we took a box. You'll get this from Amazon. Make a hole. We took a big one, 12, 12, 12. A 4-inch hole. This is the smoke machine they use. You can use agarbattis, it works. Take some 4 or 5 agarbattis, burn it and put it inside. It gets filled with smoke. So now when you hit the box, because the box compresses, the smoke comes out. Let's see that in slow motion there. See that when he slows it, hits, what comes out is a disc. But remember, the center is going the fastest, the edges are going slow because they got dragged by the edges of the box. As it goes, can you see the ring? That's your ring. So the more it travels, the center will become more empty. You can see a more ring shape. So end of the day, you're hitting with a water ka thing, air ka set. Yep, you can play such things. It's actually called a vortex cannon. So, in US and all, this police are testing, something called a vortex cannon. Like instead of water, Can we use air, and hit people and disperse them? This is a Lord of the Rings. I'm sure you must have seen. Now, there, he takes out. Now, that is viscosity. See? That is science. This is magic. We don't study this. Right. So, yeah, we don't have a school for that. You have to go to Hogwarts. So, we don't study that. Clear with the velocity profile? Have a look at this picture. So, the liquid layer, it is in contact with a solid which is going with V1. That layer also will have the speed V1 and so on. Let's see a question. So we have a plate here which is going with 2V. We have one more plate here which is going with V backward. And this entire space right in the middle is filled with liquid. Viscosity is zeta. You kept a plate in the middle of this and you started pulling with F. Let me show you in the side view. If I just show it in two side view, it looks like this. This guy is going with 2V. This guy is going with V. Somewhere in the middle here, this guy is being pulled by a force F. And it is also traveling with velocity V by 2, which is constant. So from here to here, this distance is d by 3. And here to here, this distance is 2d by 3. So this entire space is filled with liquid with eta viscosity. Area of cross section is A. So the question is, find F. So how much external force are we applying to pull out the plate with constant speed? That's your first question. Second, where should the plate be placed? So if instead of keeping it d by 3, 2d by 3, can I keep it somewhere else such that it moves with v by 2, but F is 0? Without applying external force. If I change the position, where should I keep it so that it can move without applying an external force? Are you able to visualize the diagram? It's like two bread pieces with a lot of jam in the middle. And let's say there's a butterka slice in the middle and you're pulling out the butterka slice. Able to visualize? When it is about food, you guys will understand everything. So, works. So there is a plate here which is being pulled apart. 3 eta AB by 2D. Just to give an idea, how many viscous force are there? There will be two. Hope that you figured out. For every surface, there is a viscous force. There is a friction between these two guys and there's a friction between these two guys. Assume the layer is thin. Huh? We are assuming D is small. Get this thing. Easy one. Simple question this is. Viscosity, we really don't have much of a models, but whatever we have after this are like little good ones. We barely have something like 7-8 problems in this. We should wrap it up soon and we'll start with surface tension after this. Should I help you with one? Eta A 9B by 4D. Let me help you with the first one, say. So when you take this plate here, again, it's all about FBDs. So there are two frictions here. Can you tell me what is the friction direction between the upper and the lower? It is exactly like friction. Ask yourself, who is going faster, 2V or V by 2? 2V. So what should the friction do? Friction should support the plank and oppose the 2V plate, isn't it? It is relative motion. Remember, friction does not oppose velocity. It opposes relative velocity. You need to see who is going faster. This question is exactly like, three blocks. The upper block is going with 2V. This guy is going with V by 2 and this guy is going with V. How do you put the frictions? Remember how to put the frictions on three block problem, right? So same way. What about the friction on the bottom? This guy is going V by 2. This guy is going V. So what will happen? This friction will be this way, F2. I hope that is clear. The directions, both the frictions won't be in the same directions. Therefore, F is equal to F2 minus F1. And what is F1? F1 is eta area relative velocity 2V minus V by 2 by distance between the layers D by 3. That would be 3V by 2, 9 eta AV by 2D. And before friction 2, it is eta A relative velocity, which is V by 2 minus of minus V by 2D by 3. Please check your signs. The area would be 3V by 2, so that is 9 eta AV by 4D. So if you subtract this F2 minus F1, I end up with minus eta AV by 4D. Minus indicates force is not towards right, but the force is towards left. Clear? I hope everyone is clear with this thing. So when you say dV by dz, remember you're talking about relative velocity. Same thing, F1, F2, they just behave like frictions. You're not supposed to oppose the velocity of the plank. You're supposed to oppose the relative velocity of the plank with that surface here. This is the first part of the question. How much force you require to maintain the velocity? The force is actually towards left. Now, the second part of the question, where should I keep this plank so that I need not apply the force? Think I'll give you a minute. Get it? Okay, Anushka, Lakshika, we have two answers. You got an answer? Please type here in the chat box to the co-host. Don't type to the host. That is my tablet. I can't see you guys. I'm looking at you guys on my computer screen, which is the co-host. We have two answers. Ronak, yep, you're right. We have three answers. 20 seconds. Right, Suchir. So think of like this. If I can find a layer which is going with V by 2, and if I keep it there, isn't my job done? When will friction come? Because you're going with a different velocity. So I can do that, or I can simply play the same game again. So I just want to create a situation where let this be x and let this be d minus x. So if you want f0, you're simply saying f1 should be equal to f2. So what is f1? Eta a relative velocity. This way is going v by 2. 2v minus v by 2 by x should be equal to eta a relative velocity v by 2 minus of minus v by d minus x. So that is 3v by 2x is equal to 3v by 2 d minus x. We get x is equal to d by 2. Easy? In the center. Check it out. Right, Yasha, you got it. Shan got it. Adrit, Suchir. Swastika, you're able to type something? I just got a dot actually. Okay. Easy? You're getting, we're just playing with that one formula there, eta A dV by dz. I hope now you understood the meaning of dV by dz. dV by dz is written between two layers. So if you have a plate between like this, like a sandwich, there's an upper surface and there's a lower surface. So each surface will have a friction. Clear? Second one. Theta, we have a long incline. On this incline, you kept a thin layer of fluid. Thickness is Z. On top of this, you placed a plank. Mass M, area A, released from rest. Gravity is there. Find velocity of the plank as function of time t. Viscosity is eta for the fluid. It's a thin layer Z. Plot VT graph, velocity time graph, acceleration time graph, position time graph. Let's get them all.
So here the liquid is fixed, right?
The liquid also will flow, but that is fine. Let it be. The liquid is everywhere.
Okay.
That layer is fixed. You're saying the layer is not flowing down, no?
Yeah.
Layer is fixed.
Okay.
Hope the question is clear, everyone. This is the same concept you use when you go to a water park. They release water and you're skidding on that. If they don't release water and if you try to skid, what will happen? When you come down, your skin will be gone. So, or you won't slide only. So you have to put enough water on that. And on top of it, if you ever see it, they'll give you a plastic sheet. You're supposed to sit on that and then slide. If you just slide with your just shorts and jump on it, high chance your skin will come out somewhere. So yeah, don't do such things and make sure there is enough water.
There at T is equal to 0, V is equal to 0.
Release from rest.
Watch it.
Let's go, everyone. Got 2 minutes. Ishan, once you're done, do switch on your cam. If this question comes in the exam and we want to guess, what will be the options? VT graph. Let's call them ABCD. 1, 2, 3, 4, 5, 6. Without solving, how do you guess? Without solving, how do you guess? I keep telling you this thing. Guessing is a very important skill. To guess, you need knowledge. If you can guess even 3-4 questions in the exam, that saves you a lot of time. And most important thing, it makes you feel good. And the second thing in guessing is what? Whenever you guess, don't try to find the right answer. If you can find the right answer, why is it called guessing? You try to find the wrong answers. That is easy. Tell me what is wrong. Happens, no? When you're seeing your friends or some relatives, it is easy to point out all the negative things. Ye auntie na bahut weird hai. She keeps on poking into everyone. This uncle na is such a guy. He just comes to eat food. See, that is more easy to figure out negative stuff. Positive things are difficult. When was the last time you praised someone heartfully? When was the last time you cursed at someone heartfully? Sure, every day. First thing, you're starting from where? 0. So the graph should start from 0. That's a basic information. This guy is gone. Remaining all are starting from 0. Okay? Next thing, think about the forces. What are the forces acting? Mg sine theta and viscous force. That's it. So initially, velocity is 0. The only one who's acting is mg. So as you're going faster and faster, what should happen to the viscous force? Increase or decrease? Viscous force will increase. If you go faster, viscous force will increase. If viscous force is increasing and mg is there, at some point you're going so fast, what will happen to your velocity? Becomes constant. You will reach a certain velocity when that mg will get, balanced by the viscous force. At that point, you can't go faster than that. You'll reach a limit. So one thing I know, the velocity should keep increasing. It's an increasing function. This guy is gone. It should become constant. So this guy is gone. You can't have this thing. This guy is definitely gone. Now looking at the function, it is mg sine theta minus some velocity thing. It doesn't look like a straight line. And if you see this thing, abruptly it becomes constant. So it has to gradually get closer and closer to, that value there. Only 5 looks little closer to all that. Clear? You should know these things, how to guess, because in an exam like mains or bits, you'll be able to actually guess the options. Because they'll give such dumb options, you can eliminate 3. And that saves you a lot of time. Especially in an exam like bits, imagine you can. I used to guess a lot. Matlab, see, again, all these are smart guessing, not random this thing. Because if in an exam like bits, if you can actually guess questions, right, you get extra questions in bits. So I finished the paper in 2.5 hours. I did 138 questions out of 150. My attempt is 150 questions. I had 12 questions, which I don't know what the hell they are. Some are English, logical reasoning, kuch bhi tha. I guessed all of them. I marked everything. 150 questions I submitted. Then you get extra 12 questions. Bits ka the thing is, if you submit all the 150 questions and if you have time left, they will give you an option to write extra 12 questions. All these 12 questions are 4 maths, 4 physics, and 4 chemistry. So my logic was, even if all these 12 will go wrong, I'll get minus 12. Physics, chemistry, maths. Physics, I'll do at least 3. Chemistry, I'll do at least 3. So the maths, I won't do even a single one because maths is my favorite subject. Right. So this 6 questions, 6 into 3, that is 18 marks. I'll still make a profit of 6 marks. I did 11 questions from those extra questions. I really don't know exactly how much, but I'm guessing my score should have increased at least by 30 marks. Now, this is not subject. This is what I keep telling you. Whenever you want to crack an exam, you need 3 things: subject, how you handle the exam, and how you handle yourself. Most people think I'm studying really well, so why I'm not scoring? Because your other 2 skills are bad. If you don't know how to handle an exam, there is no point. I told you, right, about Sabir, remember? My classmate, who is better than me in physics, who never scored more than me in physics. That is how it goes. So when we wrote the AIEEE exam, my rank was already 185. His rank was 9,000. Advanced, luckily, I got 360. His rank was 660, 670 something. When the paper became tough, he started getting an advantage. How do we do this thing? Start with the free body diagram. What else? Mg sine theta, the viscous force, and the acceleration. And the viscous force will be how much? Now, if you take this layer here, This surface is going with V, and remember this is at rest. So viscous force F will be eta A dV by dz, that is V minus 0 by Z. So that is eta VA by Z. So that's your viscous force, which is increasing with velocity. Mg sine theta minus friction is equal to Ma. Only thing is friction is not constant like solids. Mg sine theta minus eta A V by Z. The moment you wrote this, physics got over. It becomes max from here. Now from here you can see eventually, after a long time, F viscous balances Mg. So if it's a mains level question, they'll ask you this: find the terminal velocity. Then you need not integrate. That is, acceleration becomes 0. So if you put A 0, you'll directly get V is equal to mg z sine theta by eta A. This is called terminal velocity. This is the velocity after a long time, that is infinity. Sometimes this itself is a question. What is the terminal velocity? But I didn't ask you that. I asked you velocity as function of time t. So then let's integrate this. So this is mg sine theta. Bring that m this side. So you end up with g sine theta minus eta A by mzv, and that's dv by dt. So we have dv by g sine theta minus eta by mz into v is equal to dt. And I hope you remember this. So dx by ax plus b ka integration is 1 by a ln ax plus b. They didn't start the integration still. This much you should know. Yeah. Now we have to integrate that and put it there. Please have a look at here. It has become a max question now. Try. I'll give you 30 seconds. 1 minute. Integrate this. Get me the answer.
You have to send the answer.
Now you can leave it. I know you can't send this. So if I integrate this guy, I end up with is this. So minus eta ln limits will be from 0 to v. This will be time. Shift everything this side. Sine theta minus this will be minus eta a time by mz. We get mg sine theta z by eta e1 e power minus. That's your velocity as function of time t. So if you put a vt graph, as time passes, it will get closer and closer to this, but it'll take infinite time to reach. This is your V terminal. And how does an AT graph look like? You start with some value. How much? You start with g sine theta because initially there is no other force. And then you decrease, eventually you'll decrease to 0. So exam they'll ask a question like this. The velocity is always increasing. Acceleration is always decreasing, which is true. What about an xt graph? Xt graph will go off like this. it will try to get closer and closer to this line. This is theta, where tan theta is V terminal. Remember, the slope in xt graph is a velocity. So this xt graph is actually getting closer to that line. The slope will tend towards V terminal. That is how the graphs look. Check it out. Right, Ronak, you typed it. Right, Aryan. Check out the graphs. So VT graph is always increasing. That itself is a statement question. This is always decreasing, but never becomes zero technically. Takes infinite time. I like the xt graph actually. That curve actually becomes a line at infinity. How does an AV graph look like? Acceleration V graph. It's actually a straight line. So this point is g sine theta. This point is V terminal. How do I know that? Check out here. Isn't it a line equation? Y is equal to mx plus c. That looks like y is equal to mx plus c, where m is a negative slope. There, that's the fourth graph. If you want AV graph also we can draw. It's a good one. Even at an advanced level, I can ask you this as a single choice question with a graph. That would be fun. It's a mains level, they can ask you a VT graph. Clear with this thing? Ali? Ali, are you there? Yeah. Anika, got this? Yasha, Vidyut? Vartika, Rehan? Clear. Any doubts on this thing? Anyone not convinced anything particular? This page, anything that you're not clear? This is the main thing. Once you got here, it is over. It is just a matter of integrating after this. Let's see one more. We have a disk. Mass m. Radius r. This is placed on a thin layer of fluid. Viscosity is zeta. So this disk here is rotated with omega and placed on the liquid. Do you remember you have done a question like this where rotation mein a disk is rotated and placed on a rough ground? I told you this will come again. Disk is rotated with omega naught and placed on a thin layer of fluid. Find omega as function of time t. Hope the diagram is clear. Take a disk of mass and radius r rotated with omega and you just place it on a thin layer of fluid. It starts gliding on that and you get a viscous force because of which the omega changes. Find omega as function of time t. Quite a good question. Again, we'll encounter this thing in magnetism, EMI. So this disk thing rotating and stopping will come in at least 3 chapters. Anyone not clear with the question, please ask me. Now you're just guessing, I guess. Think about it, Ronak. If you put t0 in your equation, what do you get? You get 0,
We
isn't
get
it?
omega naught.
If you put you wrote 1 minus eta 8. Okay, that is not exponential, yeah? So that is definitely wrong then. The- I thought at least you typed an e there. Then it is gone. You can get a feel for these kind of functions, The faster you rotate, more viscous force you have. More viscous force you have, the more deceleration you have. More deceleration you have, the velocity will decrease more. So if you see this function, right, it is killing itself. By applying more friction, your velocity is decreasing much faster. If velocity decreases, friction decreases, we won't decrease as much as before. Can you see what is happening? This function is killing itself. These are called as decay functions. And mostly 99% they'll be exponentials. So that should give you a biggest clue. 1 minus e bar. Gone, boss. Look at your answer. If you typed the answer as 1 into e power minus something, just ask yourself, if I put t0, I get 1 minus 1. That means I get 0 at t0. Is the disk at rest initially? No, your option is gone. That's what I'm saying. See, when you write an answer right, make sure you know what is a blunder. Wrong, you typed one more thing. Great. Now ask yourself, eta a time by z, is this a dimensionless quantity? If you write e power this, shouldn't this be a dimensionless quantity? That's not dimensionless quantity. This is one of the important skill. It's okay if you don't know the answer. You should know what is a bullshit one.
So divided by
Now you're setting up the answer. Doesn't work that way. Try. Try that for the next question. You want? I can make this more deadly. Or kuch nahi hai. Instead of this question, I'll just say like this. There's a cylinder like this. There's a liquid in this gap. Find omega's function of time t. You'll be dead. So let's focus on the subject. Just to give you an idea, right? How we did this in rotation. Remember this. How did we do this? See, this is what I was saying. Learn this skill. You should know like in which chapter we have seen this kind of thing. But what did we do there exactly? There, we took a small ring. Then we found the friction there. In this case, friction was mu into mg. And then we found the torque on the ring. Then we integrated, we got the torque on the disk. From there, we got alpha. Then we said alpha is constant, so we use this. You should learn to take concept from some other chapter and see how much of it is valid here, where you need to adjust and where you need to change. If you can't do that in physics, you will think every problem is new. You will get overwhelmed and you'll get frustrated. When you're an architect or tomorrow in mechanical engineering, you're designing new engines. Your first homework will be they'll give you some 100, 200 engines and they'll tell you study these 100 engines. Not because you're going to copy from them. Tomorrow, when you have a new issue, they want you to take ideas from these 100 engines and try to implement something new. Physics is no different. How do we go about this? So one thing is clear. We have to take an element at a distance x, ring. Try. I'll give you a minute. Just give it a try. I'll just get some water and come. Let's see. So let's start with an element at a distance x. Take a thin ring of radius x and thickness dx. So if you assume this guy is rotating with omega, so this is v is how much? X omega. Remember, the viscous force will be backward, opposite to this. So you are comparing here with the ground. So the viscous force, again, remember, this is a tangential viscous force. If you take the total force, it will be 0 because it gets cancelled out. F viscous tangential will be minus, I'll not the minus sign is already taken care. Eta, area is 2 pi x into dx into velocity profile is x omega. The ground is 0 and the thickness is z. Please have a look at that thing. Eta a dv by dz. A is the area of the ring, okay, and dv by dz is the relative velocity between that ring and the ground and the distance between them, which is z. So this is 2 pi eta omega y z x square dx. So torque on the ring will be the radius into the F viscous on the ring, which is 2 pi eta omega by z x cube dx. Then here take torque on the disk. You can't take each ring separately. If you take each ring separately, then there's a normal reaction between them. I don't want that. And all the entire disk is going with same alpha at any point of time. This will be 2 pi eta omega by z x cube dx 0 to r. So we end up with pi eta omega r power 4 by 2z. This is your torque as function of time t. This is the viscous torque. Great. And then we can write, once we got this torque viscous is equal to I alpha. That is pi eta r power 4 by 2z omega. I will be mr square by 2. It's a disk. Alpha will be minus d omega by dt because it is decelerating. Torque is opposite to that omega. So from here we get d omega by omega will be, we will cancel minus pi eta r square by mz dt. This goes from omega naught to omega and this goes from 0 to t. So this gives you omega naught into e power minus eta r square by mz into time. Check, that's your answer. Pi eta r square. Yeah, Suchir, I think 1 or 2 terms are missing. Please check how I did this thing. So here I'm integrating with x. Here I'm integrating with time. So when you integrate with x, omega is constant. You're finding the torque at a given omega. If you see till here, it is the same thing which you did in rotation. The difference is because the torque is changing with omega, I can't use the kinematics equations. I have to integrate. That became the different thing. Alpha was not constant here. Alpha is changing with omega. The faster you go, the more deceleration you have. Please check. Any step you're not convinced, ask me. Arjun, Aditya, got this?
Yes, sir.
Adrit, Anusha? Clear? Palaksh, Neil? Swastika? Clear, na? Maulika, got this? Utsa, clear, na? Vartika? Great. Going ahead. Vidyut, clear na? Going ahead. Perfect. Next one. We have a cylinder which is fixed. So inside this, you kept another cylinder coaxially in the same axis. Which is rotating with omega, which is constant. This is a solid cylinder. And the space between them is filled with liquid, eta. Let this radius be R1, let this radius be R2. The radius are also different. The outside one is a fixed cylinder, and the length of this entire cylinder, let it be L. A solid cylinder, mass, I mean, you don't require mass actually. Okay, but we'll give it off. And radius R1 is placed coaxially meaning the same axis. Inside a fixed hollow cylinder. Of radius R2 filled with liquid as shown. First one. Find velocity of the layer at a distance x. Where x ka value lies between R2 to R1. Remember, you can't use that dv by dz. It's not a thin layer. So dv by dz won't be equal to v2 minus v1 by z2 minus z1. This is not valid anymore. This is not a thin layer. Second, find the torque. Now see, this thing is like, you know what? Ever seen this thing? In the buttermilk, they keep that thing and they do churn the buttermilk. Kind of looks like that if you see. So find the torque external required to maintain the omega. Because if you rotate the cylinder and leave it, eventually it is going to stop. So I want to know how much torque do you need to apply to maintain that fine torque external required to maintain that omega, and find the heat produced per second. So if there's a viscous force, there is also heat. Let's get these three. I hope the diagram is clear. This is something like, you kept the buttermilk, you keep it in that thing and you start rotating, you churn the buttermilk. Kind of looks like that, kind of. But this guy is just rotating with constant omega in one direction. How do we proceed?
So not a thin layer is just for subpart A or also for PNC?
Everything. R2 minus R1 need not be thin, na?
Yes.
Until and unless mentioned, don't assume it is thin layer. If you see in every question I was mentioning. So there's no guarantee it will be thin. So if it is thin, they will say R2 minus R1 is much smaller than L. How do we think? Let's see. How do we start? Let's try to understand the diagram. In this, each layer is going with different velocities, right? Each layer is actually going with different omegas. You can say that. So when you take this, consider a layer here. At a distance x, take a thin layer dx. Now, if you look at this in the top view, so how is the friction acting on this layer here? If your omega is that way, the friction will be like tangential. It is going in a circle like this. So the liquid is rotating, the friction will be in the opposite direction. If you look at this in the top view, if you see here, on each layer, if this is a torque, the same torque will be on this, and this will be torque. I'm getting it. I'm not drawing all the layers. So the torques will be acting on both the sides. The inner layer is pulling the outer one, and so on. So torque due to viscous force is same on each layer. Why?
So how?
That is what I'm asking you. What, how? Have some patience. Why should the torque be same? Meaning, if you take a layer in the middle, this guy and this guy are pulling and pushing with the same torque. Because if you see, omega for each layer is constant. Omega is changing from layer to layer, okay? Think about this. This outermost thing is almost at zero velocity, isn't it? The layer in contact with R2 is not moving only. The layer in contact with the cylinder is going with how much velocity? R1 omega. So this guy is going with R1 omega. This guy is going with zero. So every layer is having a different omega, but it is constant for that layer. Therefore, alpha is zero angular acceleration. Therefore, net torque should be zero. That means on each layer, the torque due to the outer layer and the inner layer should be equal. Is this making sense? If you take this layer, there are two torques actually. One torque is from inside and one torque is from outside. So each layer has a different omega, but all layers have alpha zero. That means on any one layer, the net torque is zero. Clear, everyone? This is making sense? Now, take an FBD of this liquid. Don't take for a single layer now. Take all this liquid here. This is X and this is R2. You're getting? So we are taking FBD of this. So on this, you will have a force F. This viscous force will be how much? This is the F viscous. You're getting what you take FBD as? Always omega different and same. Are God. It's like this inner layer will have omega 10, outer layer will have 20. Let's say this is 30, this is 40, this is 50 SR. Each radius X will have omega constant, but it is different for different X. Understood? Omega is not changing with time, it changes with position. Does it make sense? Just like, steady flow in fluid mechanics, velocity of each particle changes with time, but at a given position, it is constant. So we will add that. See, omega is changing with position, but constant with time. Anyone else? Someone said, how are you convinced?
Yes, sir. Yeah.
So on this inner layer, the F viscous will be how much? Eta. Area will be 2 pi x into L and velocity profile dv by dx, which I don't know how much it is. So torque will be x into F viscous. I'll just write FV, which is 2 pi eta L x square dv by dx. But luckily, just now we proved the torque is constant. I don't know the value, but I know it is constant. Fair enough. So I can write now this thing as torque dx by x square is equal to 2 pi eta L dv. Integrate on both sides. This thing, the velocities will go from where to where? The velocity will, I can take this thing as R1, and here the velocity will be R1 omega, or I'll do one thing, I'll take R2. R2, this guy is 0, this is V, and this is some X. So this will give me torque minus 1 by X. So minus 1 by X, limits will go from X to R2, 2 pi eta LV. So this will be torque is 2 pi, or 1 by R2 minus 1 by X is equal to 2 pi eta LV. Clear? Did I miss something here? Looks right. And it is 0, it is R2, and it is V, it is X. Fair enough. Or I'll do one thing. Let me find the torque only first of all. Yeah, this is fine. So from here I got torque is equal to that minus sign. Nah? I don't want that minus sign actually. Where am I goofing up a minus sign? It is opposing the velocity now. Torque. This is 1 by X minus 1 by R2. So see what we got here. So we got torque is 2 pi eta LV by 1 by X minus 1 by R2. Since it is same for everyone, if you substitute X is equal to R1, we will get the total torque. Isn't it? So when X is equal to R1, I'll get the torque value. This will be 2 pi eta LV by, what is this V exactly? This V is R, velocity of the layer, no? When X is equal to R1 and V will be equal to R1 omega, substitute there.
So won't that be 1 by R2 minus 1?
1 by R2. No, there is a one more minus sign here. The negative sign indicates, it is opposition, right? We didn't take care of that negative because, see, X is always smaller than R2. If I get 1 by R2 minus 1 by X, I'm getting a negative value. We forgot a minus sign. This is 1 by R1 by 1 by R2. Is this clear? Or I can do it another way. What I can do, right? I can directly here only put the values of R1 omega and R1. Yes, the torque value directly aa jayega. But then again, I have to integrate and show you that the velocity is a function of X. So I did it like this. So from here, I'll end up with 2 pi eta L R1 square omega by R2 minus R1. This is a constant torque, which is acting as function of time t, which is constant. This is your external torque.
So R2.
एक R2 भी था ना. Now how to find the velocity? Here, get back to this. So from here, we can get velocity V is equal to torque into 1 by X by 1 by R2 by 2 pi eta L. This is the velocity as function of X. This is the first question. Find the velocity of the layer at a distance X. This is the second question. Find the torque, external force required to maintain omega. What is the heat produced? Heat per second is nothing but power due to viscous force or viscous torque, which is torque into omega. Again, what did I do? Listen, first thing I needed to prove that each layer ka torque is same. You're getting it? So if you take an inner layer like this, there are two people pushing out in and out. It's like there is one layer here inside. That guy is giving some torque. There is this one layer on the outside that is giving torque in the opposite direction. Both of them should be equal. If they're not equal, then there'll be an angular acceleration. That means each layer ka omega is changing continuously with time. I hope that point is making sense. If each layer ka omega is changing, system is not in steady state. The meaning of steady state is what? It doesn't mean all are going with same velocity. At a given position, the velocity should not change with time. Isn't that the meaning of steady state? So every layer has an omega, which is constant for that layer, but different layers have different omega. Therefore, alpha for each layer is 0. So from there, we proved eventually the torque, whatever we get on any one layer, should be equal to the torque due to the external force. Then we said, take an FBD of the liquid. This is an FBD of liquid, not for a single layer, from X to R2. You took the entire bulk of the liquid. So now the inner surface will have a friction. Getting it? That will be F is equal to eta A dV by dz. So that friction into X will give you torque. But I know torque is constant, so I can keep it aside and integrate. I got velocity as function of X. If I put X is equal to R1, then velocity should be R1 omega. From there, I'll get torque value. Then I got everything else. Can you see here? Velocity is not a linear function. It is 1 by x square function. If you look at this dv by dx, dv by dx is actually proportional to 1 by x square. That itself is a question. This is not a linear function. How is the velocity gradient variable? Please check, everyone. You guys should definitely try this on your own today after the class. Take a rough paper and try to do this thing. Clear? Take a break. Come back by 7 2. We'll continue from here. Any doubts so far? Anything not clear? Please ask.
Sir, after the cylinder stops rotating,
Cylinder never stops, God. Constant omega.
but it won't have like two directions of torque.
Find torque external required to maintain omega. Torque will not, cylinder will not stop. Problem kya hoga? If the cylinder starts stopping, then omega will be changing with time. Then each layer will have an alpha. I didn't want to get into that part where you get torque 1 minus torque 2 will be net torque, and that will be a mess. Keeping omega constant only, you saw how deadly it became. Now, if you want to mess up that omega, things will be more deadly. Let's not get into it. Clear? This will feel little weird because you guys got used to the dv by dz. Na? You never had a problem with that. You simply wrote v2 minus v1 by z. Suddenly it changed, so it started becoming a mess. Let's see one more like this later on. Take a break. Come back in 10 minutes.
Sir,
Suchit.
so the heat produced will be equal to the
Power
supply.
produced by the external force. Yeah.
Okay.
This is also the power supplied by the external force, no? Because what is happening to your energy which you are giving? Because no one's speed is changing. Isn't it?
Yes, sir.
Yeah. For torque external. That's it. Why logic? Anyone else? Anything else? Okay, come back by 7 2. We'll continue. So we have a cylindrical pipe here. Here the pressure is P1. Here the pressure is P2. So delta P is P1 minus P2, which is the difference, pressure difference across the pipe. The viscosity is zeta, density is rho. So this center is your actual line. X is the distance from the axis. So what is happening here? We have a pipe here, and inside the liquid is flowing in a steady state. You're getting? Now, because there is a viscosity, the liquid won't go on its own. You have to apply some pressure for the liquid to push through. Making sense? You have to apply some pressure so the liquid will go through because there is a friction. Find velocity of the layer. Distance x from the axis. Assume the layer in contact with the outer surface is at rest. So we are assuming this outermost layer, which is touching the cylindrical pipe, is at rest. Find kinetic energy of the liquid. Pipe ka length is L. To find the kinetic energy of the liquid in the pipe. Find the volume flow per second. How much liquid is flowing out of the pipe every second? At what distance or what x? There's a maximum flow per unit thickness. Meaning from every point, the liquid is coming with different speeds. So, so if I tell you like this, you have to take a bucket and go and stand. There is one particular point where if you go and stand with a bucket, maximum amount of liquid will come per second. First, let's get the first three parts. D we can do from there. So we have a pipe of radius r and length L. Inside there's a liquid of viscosity eta and density rho. Because there's a friction, liquid won't go on its own. Someone has to push it. How do we push it? By applying external pressure. So we are applying pressure P1 on the left and pressure P2 on the right. So the difference in pressure is P1 minus P2. Because of this pressure, the liquid started moving. But last time, I showed you in the beginning, the edges will be at rest. As you get closer, it goes faster. So the liquid is actually flowing like this. It flows faster in the center and flows slower on the edges. So find the velocity of a layer at a distance x from the center. If you got that, you'll get the kinetic energy, you will get the flow, you'll get everything. The first part is the main one. Get this. This is a proper advanced paragraph level question. Anyone didn't understand the question, please ask. Think. How will you proceed with this? How do we start? This and the previous one, they're not same exactly. I'll give you a hint. See.
So I got the answer, but just, a little bit.
Oh, just give me the D part, no answer. If you got the D part, then you must have got everything. D is this thing at what distance x max flow per unit thickness. Try. Try now. Others also have to try. I'm just giving them a hint. By the time I explain the hint, you get 1 more minute. So take FBD. Don't take FBD for a layer. Take FBD of a cylinder. Now on this cylinder of radius x, tell me what are the forces acting? P1 into area pi x square. From this side, you're pushing P2 into pi x square. And how will the friction be? The friction will be tangential on the surface. Now friction will be like this. That will be F. Isn't it? Think of like this. It's like, if you're catching your pen and someone pulls it out of the hand, how is the force on the pen? The pen ka force is only on the surface, isn't it? The viscous force is acting only on the surface of the cylinder, whereas the force due to pressure is acting on the entire cross-sectional area. Is that clear? Okay, let's see. No, Ali, that's not right. Again, remember, each layer has a constant speed, which is different for different layers. So here also acceleration is zero. Steady flow, no? So what is this viscous force? Eta area will be the surface area of the cone 2 pi x into L dv by dx. That's your velocity profile. I hope that is making sense. So the pressure will act on the cross-section area, whereas the viscous force will act only on the surface area. So this will be delta P into pi x square should be equal to friction. This will be 2 pi eta L x dv by dx. So dv will be pi will cancel. Integrate. This will be r, this will be 0, this will be x, this will be v, because velocity is 0 in the outer layer. So v is equal to delta p by 2 eta L 4 eta L x square minus r square. delta P is P2 minus P1. That's a convention, na? Final minus initial. So you will, this will be P1 minus P2. P1 is greater than this. So you get a minus sign. That's your velocity as function of x. So each layer is having a different speed. This itself is a pretty good result. And you can clearly see here, dv by dx is proportional to 1 by x. Not a linear function. There, you got the first part. What's the second part? You want kinetic energy? So take a thin cylinder with dx. So this entire layer is going with V. So kinetic energy of this thin cylinder is half dmv square, which is half density. This will be 2 pi x thickness into length. This is a mass into v square is this guy. So kinetic energy of liquid, just integrate this.
So how is dv by dx proportional to 1 by x?
Oh, sorry, proportional to x actually. This is an x square, na, forward to cancel.
Hmm.
Delta p square 16 eta square L square. I will leave the working here. This will go from 0 to r. You can integrate this. It is just x power n integration. You'll get the answer. Check it out. So once you got the velocity, you'll get the kinetic energy. Question still not over. The third part, how much liquid is coming out per second? That's the main one actually. Try. Let's calculate that. Find the amount of liquid that is flowing out of the pipe every second. Any doubts on these steps? Please ask me what we did. We draw an FBD for a cylinder of radius x. So the pressure will act on the cross-sectional area, whereas the friction force will act on the surface area. Any doubts on this page? Clear? Anyone got the volume flow per second? The same. What is volume per second? Remember, area into velocity. Area into velocity will give you the volume flow. So find the amount of liquid coming out in one small cross section and integrate the whole thing. This integration will be pretty big one, I guess. Like x power 5 is also sitting inside. That's fine. That is just anyway x power n only. See? So take a thin cross section here of radius x and dx. So velocity v is coming out from here. The volume flow per second through this thin circle or thin cross section is how much? Area into velocity, which is 2 pi x into dx into v. 2 pi x dx into v. V is this guy, delta p by 4 eta L into r square minus x square. This was liquid is coming out every second through dx thickness. This actually leads to the fourth question directly. So this guy will be delta p pi by 2 eta L dx. This would be r square x minus x cube. So for the fourth question, you're asking for maximum flow. This function should be maximum. D by dx r square x minus x cube should be 0. This guy would be r square minus 3x square is equal to 0. X is equal to r by root 3. See what is happening here. At the center, speed is maximum. But what is the area? Almost 0. At the outermost edge, what is the area? Maximum. But what is the velocity? 0. You get the catch? The volume flowing per second is area into velocity. The more you go outside, you get bigger areas, but the problem is your velocity is also decreasing. So r by root 3 is a spot where the liquid flows, maximum amount of liquid comes out per unit width. Means if you divide this entire cross section into small cross sections of dx rings, the ring at r by root 3 gives you the maximum amount of liquid per second. Is that making sense? So that x is equal to r by root 3, max flow of liquid is there per unit width. We're still into the C part actually. For C part, we have to integrate this term now. Please have a look at this page. Now, if I integrate that term there, so the total volume flow per second is integral delta p pi 2 eta L integral r square x minus x cube dx. Will go from 0 to r. This turns out to be r cube minus r square x, so it is r power 4 by 2 minus r power 4 by 4. This turns out to be pi delta p r power 4 by 8 eta L. This is called Poiseuille's equation. I hope you studied that. So whenever you have a pipe with viscosity, the volume flowing through the pipe is given by pi delta p, radius power 4 by 8 eta L. You definitely need to mug up the result. Very important. It's okay if you don't know the derivation for mains and bits. This is what we call as Poiseuille's equation. I'm pretty sure I wrote the spelling wrong, but okay.
So can you go to the previous page for a minute? Yes, sir.
I'm sure you must have seen this equation somewhere. This is the derivation for that. Clear with this? I added a few more questions on this thing, like kinetic energy and the maximum flow rate at a distance x. Again, one of the rare equations in physics where you have power 4. Clear? Just a matter of integration afterwards you got this. Now, this equation you can compare with Ohm's law again, just like what we did in conduction. So you can replace this with a resistor R. Let's call this small r. So if you see the volume flow dV by dt, it can be written as delta P by 8 eta L by pi r power 4. This is the volume flow per second. That looks like current. This is similar to current. What is current? The flow of charge. It is the flow of liquid. This is similar to potential difference, so pressure difference is similar to potential difference. So this thing looks like I is equal to V by R. So this term looks like thermal resistance. This is the resistance to liquid flow. So you can replace this whole thing with the formula 8 eta L by pi R power 4. So whenever you have pipes, you can just replace them with this resistance and solve it like circuits, which we did in heat transfer. Everything you did there works. So if you have two pipes in series, let's say length L1, radius R1, radius R2, length L2, you can replace this with two resistors. R1, which is 8 eta L1 by pi R1 power 4, and R2, which is 8 eta L2 by pi R2 power 4. Therefore, R equivalent is R1 plus R2. So here the final formula will be volume flow is delta P by R equivalent. How do you say two things are in series? They should have same current. Here it should be same volume flow. If two pipes have same volume flow per second, side by side, we call them in series. Parallel, resistor, resistor, R1, R2. 1 by R equivalent is 1 by R1 plus 1 by R2. What should be same for them? Same pressure difference. Please check. Clear? Now we can also use this for Wheatstone bridge. Even that works. Now this whole thing will start looking like conduction, current, electricity. Everything you did there is works here. Only thing, instead of heat flow per second, we have volume flow per second. I hope you remember the Wheatstone bridge. R1, R2. If R1 by R2 satisfies R3 by R4, then R5 can be removed. Check it out. That's your second concept, Poiseuille's equation. We derived it. Again, we just derived it from the Newton's law of viscosity. Clear? Let's see some questions. You will remember there'll be a lot of similarity between, this and the heat transfer questions. Similarity, yeah, same questions only. So we have two pipes here. Length L, length L. This radius is A and this radius is 2A. So here the pressure is 2P naught. Here the pressure is P naught. So liquid is flowing through this pipe and viscosity is eta. This is your interface. Find the volume flowing per second and the pressure at the interface. If you remember the same question there was, unsolved Wheatstone bridge, we will do it in current electricity. Right now we won't do it here. We'll be solving those things later on. Find volume flow per second. Pressure at interface. Remember what is the resistance? 8 eta L by pi r power 4. This is the resistance to the volume flow. Try this. In case if you have not revised the notes, you will find it that way. But if you see the notes, this was the first question actually. Second one, same thing. Heat flow per second. There is volume flow per second. Temperature difference, pressure difference. Get this, easy one. Thirty-three P by 17. Okay, we have one answer. Others? P naught is P naught, why are you getting in terms of, okay, volume flow did you find? Yeah, okay. 2 pi naught. Okay, let's see. Convert them into resistors. So let's call this guy R1, which is 8 eta L by pi a power 4 is 16 a power 4. R2 is 8 eta L by pi a power 4. Now for simplicity, if I call this guy as R, this guy will be 16R, isn't it? Keeps my life simple. So R equivalent is 17R. So the volume flow is the pressure difference by R equivalent. I can use it like current, which is nothing but 2P naught minus P naught by 17R. That's your volume flow. You can substitute R ka value. Now, if you look at this point ka pressure is 2P naught, this point ka pressure is P naught, this point ka pressure is Px. What is same in both of them? The current. So I can write current is the pressure difference across the resistor 2P naught minus Px by R should be also equal to pressure difference between the other resistor Px minus P naught by 16R. Hope that makes sense. The pressure difference across one resistor by the resistance should be the current. That should be equal across both of them. Simplify this, RR will cancel. Since anyway I want a ratio only, so R ka exact value won't matter. 2P naught minus cross multiply 32P naught minus 16Px is Px minus P naught. So Px will be 33 by 17 P naught. Yep. Right, Ishan, Lakshika. So if you got it right. Please check. Ronak, you also got the same thing. Yep. This is the pressure at the junction. Easy one. If you remember, same thing we did in heat transfer also. The temperature difference by resistance will give you the heat flow per second. Yeah, next one. Any doubts on this? Anyone who didn't get this thing? Anika, clear with this? Abhinav? Swastika?
Yeah.
Neil? Clear? Vartika, got this? Vidyut? I hope you remember this one. So we have three pipes. A, B, C. Pressure is 3P naught, pressure is 2P naught, and pressure is P naught. This point is D. So this length is L. Let's say this length is 2L. This length is L. This length is also L. This is radius A. This is radius 2A. And this is radius A. Find the pressure at D and the volume flow in each cross section. That's what I said. The questions are quite similar. Instead of place of temperature, it became pressure. $69P by 35. Okay, let's see. Try everyone. 69 by 33. Let's see. So first, let's make this into resistors. You can just replace the pipes with resistors. So this guy, let's call it R1, which is 8 eta 2L by pi a power 4. This is R3, which is 8 eta L by pi a power 4. So I'll call this R. Then this will be 2R. Then this will be 8 eta L by pi 16 a power 4. That will be R by 16. So this is 3p naught. This is 2p naught. And this is p naught. So I will write I is equal to I1 plus I2. So whatever flow is coming from 3p naught, it goes to B and C. So I is equal to I1 plus I2. So what is I? Pressure difference, 3p naught minus PD by 2R. So no need to write that entire term. Anyway, it is a ratio, it will get cancelled. I1 will be how much? PD. So remember always the liquid flows from initial to final, high pressure to low pressure. So PD minus 2p naught pi R by 16 plus PD minus p naught by R. R cancels off. 3p naught minus PD by D. This guy will be 16 PD minus 32 P naught. PD minus P naught. Bring all PDs to one side and 3P naughts to one side. So that will be 33 plus 1.5. 34.5 P naught. PDs will be 17. 7.5 PD. So 34. That guy is how much literally? 69 by 35. Yep. Once you got this, put the PD back in this equation, so you'll get I1, I2, capital I. That is the liquid flow in each section. Numbers are bad, but if you remember, isn't that the same thing we did in heat transfer? You can see a lot of resemblance. So Poiseuille's equation questions are exactly same. So there is nothing new that you will learn as such, except for that formula has changed. Let's see one more. Clear? Next one. So we have a liquid flowing through pipes. This is L and the radius is A. This is 2L, radius is A. This is 2L, radius is A. This is 2L, radius is A. 2L, radius is A. This is also L and A. I change the values a bit. So let's call this point A, B, C, D, E, and F. So pressure here is 2P naught and pressure here is P naught. Find the volume flow per second and the pressure at BCDE. Center pipe is also 2LA. So only the corner pipes are L and A, but all the other 5 pipes in the middle are 2L and A. Get this, Wheatstone bridge. Not volume flow is P naught by 4R. Okay. Fair enough. Get the pressures. Try. You got a minute more. You can just define R as, 8 eta L by pi A or something like that, and then write everything in terms of R. That will always make your life easy. Don't try to write that entire thing. It will be a big mess. You can always substitute in the end. P by 4R. Okay. Pressures are 2P, 7P by 4, 6P by 4, 5P by 4P. Okay. Looks fine. Let's see. Try. Only got a minute. Let's see. Let's see. So let's just replace this with resistors. So first let's call R as 8 eta L by pi A power 4. Let's keep that way. So this guy will become R. We can remove the middle one because it's a Wheatstone bridge. We are not writing it. So this is R. This is 2R. This is 2R. This is 2R. This is 2R. And this is R. CD can be removed. Wheatstone. So what's R equivalent? So this guy and this guy series, and they're in parallel. So 2R will be 4R, 4R will be 2R. So this is R, this is this will be R, 2R, and R. Therefore, R equivalent will be 4R. Therefore, the volume flow per second, I will be delta P by R equivalent. Pressure difference is P naught by 4R. That was easy. Now, finding the pressures at the interface, this each section. So this is 2P naught, this is P naught, this guy is B, C, D, and D. Now see, let the current flow be I. So that current flow will split here I by 2 by symmetry. This also will be I by 2. This also will be I by 2. This also will be I by 2, and I comes out. And we already know I ka value is P naught by 4R. So when you write for the rod AB, the current I is the pressure difference to P naught minus PB by R. Substitute here. P naught by 4R to P naught minus PB by R. RR cancels. We end up with PB is equal to 2 minus 1 by 4. That is 7 P naught by 4. Similarly, you can do for BC. This would be I by 2. This would be PB minus PC by 2R. 2 will cancel. This will be P naught by 4R. P naught also will cancel. PB is 7 P naught by 4 minus PC. So PC is 3 P naught by 2. Kind of expected. Symmetry left and right is the middle point. And if PC is equal, PD is also equal. That is the reason you removed it from the Beatron bridge. And for E and F, I will be PE minus P naught by R. This is P naught by 4 and PE is minus P naught. So pressure at E is 5 P naught by 4. Please check. It's just brute force. There's nothing there. You just have to literally solve for each section. So you take the current in each section, the pressure difference by resistance will give you the current in that thing. So that should give you the pressures. Clear? Any doubts on this? Last one for the day. Easy one. We have a cylindrical container. There. So liquid is flowing out like this. So container is fully filled. The viscosity is eta, right? So when the liquid is flowing out through this pipe, this is length L, this is L, this is L. So distance between any two pipes is L. So what is observed, the liquids are having different heights. Let's call this H5, H4, H3, H2, and H1. The outside pressure is P naught. So assume the volume flow is very small. You can assume the liquid is coming out, with constant velocity. Find relation between H1, H2, H3, H4, H5. The liquid is flowing out here. What is the relation between the 5 heights?
Like, sir, AB, GB, or what?
Just give me the relation between them. Find H1 in terms of H2, find H2 in terms of H3, find H3 in terms of H4. Happy? Get that. Any answers? What is same in each cross section? GP near volume flow per second, right? The same liquid flows through each cross section. So can I write like this? The volume flow per second is P5 minus P naught, the total difference, and the length will be 1, 2, 3, 4, 5. 8 eta 5L by pi r power 4, which is same as P4 minus P naught by 8 eta 4L by pi r power 4. So on, I can write this thing as P1 minus P naught by 8 eta L by pi r power 4. So then what is P5? P5 is nothing but P naught plus rho GH. So P5 is P naught plus rho GH5 because that liquid in that vertical thing is still at rest. So this guy would be, all this denominator will cancel. We get rho GH5 by 5, rho GH power 4 by 4, rho GH3 by 3, rho GH2 by 2, rho GH1 by 1. So there, so H1 is H2 by 2, which is H3 by 3, which is H4 by 4, which is H5 by 5. I don't know what is this. Then the ratio 1 is to 2 is to 3 is to 4 is to 5, isn't it? They're just linear. Easy. So if you actually draw a line now, here, you'll observe all these things will form a straight line. The gradual decrease. Easy, everyone? Got this? A simple little fluid mechanics and viscosity thing. Clear with this? So after this, we have a concept called Stokes' law. It's again a small one. It's more theoretical. We have one or two problems only on that. So next class, mostly in the first half, we will finish with viscosity and we'll start off with surface tension. Like I said, these are small chapters. Viscosity, surface tension, elasticity combined is one chapter. So the first part is the viscosity here. So they're not tough, but the thing is, it is a little difficult to start visualization because viscosity and all, you really can't figure out unless, mathematically it makes sense. But when it comes to equations, it is a little weird. Okay, so with that, we'll wrap up for the day. So we'll catch up again next week on Wednesday, same time. We'll continue from there. So any doubts in today's class? Any other doubts you can ask me? I think in the paper there are 1 or 2 errors. You can send, some of you have sent it to me. I'll do the correction and post